All right, guys, so we're going to move on to magnetic fields and magnetic forces. So we use magnets all the time. Everybody knows that. There's all different kinds of ways to do it. Elementary school art on the refrigerator, picking up lost steel screws and nails, data storage, all kinds of things. I want to get to the root of where magnetism comes from. We've got a North Pole here and a South Pole there. Here a pole, there a pole, everywhere North Pole. And let's say we cut it in half every time. And then we cut that one in half. So we cut it in half and we cut it in half again and we keep cutting it in half. And we get all the way down, we get all the way down till we can't cut it in half anymore. Why is that? Because we're left with a South Pole here and a North Pole here, and it's one atom thick. How are you going to cut up an atom? You can't. So we've got nothing left really but one atom thick. So let's look at it from the side. And we'll put our South Pole down here, our North Pole up here. And why? Let's just look at the one atom. We've got our nucleus of the atom, ferromagnetic material. And we've got E, electrons. Some of them are coming at us and some of them are going into the page. And they're just circling this nucleus. And the current is such that if you put your thumb along this current here, you'll notice that the B field points in this direction. So that is our B field. So we have now figured out that our B field is generated from a current. Current flow generates a magnetic field. Okay, so done deal. Made short work out of that. So we can do something. We can run current in a wire. And then we put our thumb along the current and we can go like this. And those are the directions for the B field. So it's going to go something like that. Our B field, okay? How do we do that? Well, it was the right hand rule that we used, and that tells us the direction of the B field. Okay, so we can use a solenoid if we want to. You guys know what a solenoid is. How do I want to do this? Here's the inside of the solenoid, and on one side we've got wires. On the other side, because it's one long wire, it's been wrapped with one long wire, we've got going in on this side current, coming out on this side current, And if you put your thumb along the current and you put your wrap your fingers, then you'll notice that our B field through the interior of the solenoid is like this. So this would be producing a uniform, homogeneous B field. Okay. However we produce our B field, it doesn't matter, but we've got some B field and we've produced it nobody knows why or how. Nobody cares. It's just there. So if we have this B field, and let's make this one a little bit nicer, that's better. We can put a charge in there. I don't want the charge. I want the charge to be this. So we have some charge. And I don't know, let's say it comes screaming in at this point. It has a velocity v. What are we going to make our charge? We'll make it a negative q. And the force, we're going to take the force, the Lorentz force. We've already talked about the Lorentz force, but in this situation, do we have any E fields around? I don't see any. So our force is simply our QV cross B. Okay, QV cross B. Well, we've got V, we've got our B, and we can do that. However, our Q is negative. So whatever we come up with for our QV, or V cross B, whatever we come up with, we're going to have to flip it and go to the other direction. So we've got our V. Let's cross it with the B. We do so, it points in a certain direction, and we make it negative, and when you do, you should end up with a force that's going in that direction. Well, that's fine, and that means that the velocity is going to change because the acceleration is going in that direction, and it's going to do something like that around some radius r. And no matter where we're at on this circle, our V is going to keep us going, and our force is going to keep us going inward. So our force is actually a centripetal force. So we could say equals MAC. And there's all kinds of stuff that comes out of that. Like tons of equations. We've got, let's say our Q minus is an electron. And MAC is MR, it's a big R, omega squared. So we've got EV B sine theta, who cares? Because they're everything's 90 degrees, all right? So sine theta goes away. to 1. Sine theta is equal to 1. So we've got our force is equal to mr omega squared. It could also be equal to mv squared over r. And that's our charge. So we can do things like we can come up with the charge per mass ratio. And that'll leave us with V over our BR. So that's our charge per mass ratio. Maybe you just want to know what the radius of curvature is, right? So then you solve for the radius. I mean, you guys get the picture. You can solve for whatever you want, but this is a how many knowns, how many unknowns? We got 1, 2. Well, this is known. So 1, 2. The mass of the electron's known. 3, 4. 4 things. So you could be given 3 things, and figure out the fourth. That's fine. Or you could figure out however we get this B field could be a question. So then you figure out the B field, and then you know the B field, and then you take that B field and then you use it for this. So there's all kinds of ways to do this. M over E, V over B. Did I do that right? We need the E and the V and the B. Okay, I think that does it. So there's all kinds of ways, right, to do these things. We could be asked for, we want a certain omega. We want to make sure that our omega is something. I don't know. There's tons of questions that come out of this. In fact, you guys did one for a homework. So that, and I think that turned out pretty well. Let's talk about, or not a homework, a test. We had it on a test. So we've got B fields. A B field. And just to reiterate, so that, you know, if somebody wasn't paying attention, it's in Teslas, okay? And you can go through and you can do the math and figure out what the B field is in units. It's a Tesla, which is a Newton per amp meter. So that's our unit of Teslas. Teslas are a small unit. Teslas are a big unit. 20 Teslas is about the maximum that we can do engineering-wise. Roughly 20 Teslas. The largest magnetic fields that we try and produce. I'm not even 100% sure where those are, but I know for our fusion reactions that we're trying to do in, say, a tokamak or something like that, those are around 20 Teslas. So I know it's hard to do. This is definitely the SI unit. However, there's a thing called a Gauss, 1 Gauss, and that's equal to 10 to the minus 4 Teslas. And this is actually a little bit more useful because 10 to the minus 4 is something that you'll see. It's an actual workable magnetic field. The Earth's magnetic field, for example, Earth's is 5 times 10 to the minus 5 Teslas. Earths. So you can see what that would be in Gauss, 0.5 Gauss. Okay, all right, so let's give ourselves some room here. B fields. Let's keep going with B fields. When we have two poles, we've got our North Pole and our South Pole. The North Pole to the South Pole is how the B field goes. Okay, so kind of looks like this. The further away you are from the magnet, the less the magnetic field is. And of course, we could do something like put a North Pole close to a South Pole, and then our magnetic field would go like this. All right. Okay, we did that already. However, I didn't say, let's go back up here and say what our period of rotation would be. If we were using omega, we'd end up with a period of rotation where we've got the mass of the electron and we're dividing it out by the charge of the electron and the B field. So, yeah. Okay. Now, we did this in class. We can do it again. Simple. We've got a simple situation. What is our situation? Let's draw it out. We've got two wires that are hanging. We've got a bar that touches both wires. Maybe the wires run through the bar. It's a solid bar, it's a metal bar, it's a steel bar, and it has a center of mass and a mass to the bar. So there's a mass of the bar. Now, up here, we've got a resistor, but it's a potentiometer. Okay, that's a potentiometer. That means we can adjust the resistance, so we can dial it in. We also have a battery that we can also dial that in as well. Okay, so we can change the current, or I'm sorry, change the voltage, the EMF that's coming out of this battery. Our current is going down on this side. It'll be coming back up on that side. And we're going to do a thing where we place that bar in a magnetic field situation. Yeah, we'll put it into the page. And so we've got some uniform magnetic field, and we've got a bar, and the whole thing is, I don't want it in blue, I want this black. We've got mg, our mass of our bar times g is equal to the force of gravity. And we can work on the actual numbers, whatever. But we also want to note that there's a length between these two, like this. Okay, there's that length. And we have one question. Well, we got a lot of questions. But which direction does the F for E and M point? Which direction? We can call this A. Which direction does that F, E, and M point? Well, where's our current going? Our current is going this direction. So let's go back to our equation. F equals QV cross B. F equals QV cross B. V is equal to delta X over delta T. So F equals we've got Q, basically we're saying I times L cross B. All right, so that is equivalent simply because of this. So yeah, nice, right? And our current is going that direction. We could call it V, but we can also call it our current. So our current's going in that direction. We've got L. L then, the vector L is going like this. So we would do L cross V. And, gosh, did I say V? I meant L cross B. So we go L cross B, and we notice that our force is up. So let's erase these guys. And we'll draw our F, E, and M. Okay, so B. For the bar to stay still in the B field, how much current needs to flow? To get to keep bar still. So, in other words, F, E, and M has to equal our FG, and we've got L cross B, the sign of 90 degrees is 1. So we've got ILB is equal to M of bar times G. And how much current? Well, current then has to equal our mass of the bar times G divided by the length of the bar and our B field. So simple. So far, so good. We can do a bunch of examples if we wanted to, but we've seen all the examples. You've done a lot of homework problems. You've done all the stuff so far, so we're going to leave it like that, and we're going to just write down ILB sine theta, just in case, you know, the angle between them is something that comes into play. So you want to know that just in case you might need it. Okay, so yeah, I don't know what else to say about that. So let's get into torque. It's this torque that is going to allow us or help us use generators and motors, electric motors. So the torque is kind of a big deal. It's also one of the reasons why electric motors have such good torque at the low end. Like diesel motors are renowned for having good torque, and I don't even think they're quite as good as they're just not. They're not as good as the electric motors. So we did it. The derivations, it's a lot of stuff. We're going to simply do a few equations here. Torque is equal to the distance d, and let's draw our circuit. We got to draw our B field. If you don't see what these things are, then it's really not going to be helpful. So there's D. The whole thing is 2D from one side to the other. And we're sending current in one side, and it's coming out the other. And let's see, what other dimensions do we need? We need this dimension. So that's L from the top to the bottom. Okay, and we've got a B field. So that's our B field that we're doing this in. So again, D cross F is our torque, because our axis of rotation is right there. So that's our pivot point, okay? And it's this bit here, this side of it, that's going to be moving with relation to that pivot point. So D is the distance from that to our pivot point. Okay, so that's that. Now, that ends up being df sine theta. And we already found out what f was, ILB sine theta, so that gives us d ILB sine theta. Okay, that's the torque, but this isn't the total torque. This is just the torque on one side. Okay, we still have the second side. So in order to do both of them, the total torque is equal to torque 1 plus torque 2. And that's obviously 2 times DILB sine theta. So that's the torque that allows us to do the things that we need. Now, let's look at it from a different angle. Let's look at it from, let's say, the top down. Here's our B field. Here's our guy spinning in the wind in our B field. And there's a normal to that surface, okay? So the angle between the normal is theta, okay? Between the normal and the B field, that is our angle theta. So because there's some area A, right? So that's the, if we go like this, that really equals n hat times A. So what is that area? That area is 2D times L. N hat. So here's our torque net equals 2 dl IB sine theta. And here we go, that's our area, 2dl. So we can say area IB sine theta. And then all you have to do is figure out which direction you're spinning in, okay? And of course, you just use your right-hand rule, and you'll get it, right? So nice. All right, let's move on. Let's move on a little bit. Okay, so we call this closed loop a magnetic dipole. All right, so magnetic dipole. And it has a magnetic dipole moment. And our magnetic dipole moment is called mu, unfortunately. Equals I don't want to start off with dipole. I want to start off with magnetic dipole moment. And magnetic dipole moment, mu, is equal to I a n hat. So we could have multiple loops. All the loops added together will all have the same area, the same current, and there will just be n of them. So now we can do a thing where we say, okay, well, our torque is equal to mu cross B, and this is for I, right? This one is for one loop, but we now have n loops with I through them, and so our torque is then equal to the number of loops times I times A times B times the sine of theta. Okay. Now, the energy. At this point, we're just going to stick the energy in where we could take this mu, we'll dot it with the B, and we'll get our energy. So mu minus mu B cosine of theta is our energy for the magnetic dipole moment. So there's, oh, didn't I just shake the world? These two guys, this one, those are important. Now we can move up. So we get to the Hall effect. Set timer for 1/2 hour. We've got our Hall effect. We've got a strip of metal, conducting metal. We've got L. We've got our charge that's going to this direction. It's a negative charge. The Lorentz force is pulling us down. It's our V negative. So we end up with our negative charge, which means if our charge is going that direction, our current is going in that direction. We've got pluses up here because the charge is wanting to go down. We've got negatives down here. And all of this is because we put it into a B field that's going into the page. So this is all inside of a B field going into the page. And we call this a cross field, the cross field case. Now, maybe I should do, I'm going to do the E field in green. So that would be our E field. Cross field simply just means the two fields E and B are perpendicular to each other. So, so we've got our force of the E field is equal to our charge E times our E field. And we've got our force of the B field, and that's equal to E times the velocity times our B field. And those actually balance out. So we get a drift velocity. Let's do E equals EVD times B, because technically what that velocity for that charged particle is drift velocity through the material. So our drift velocity ends up being E over B. And you guys have seen it already. We know that that ends up also being our C. E over B is equal to C for a photon. So nice, it all hangs together. So good. Our current in this Hall effect, our current is equal to the number of, we're going to call them electron holes. We won't put a negative on our electron. We'll call it a hole. We'll keep it positive. And this is the case. Do I have a length for this thing? Did we give it a length? We got an area. We got a distance. Let's see what happens here. So this is true, and we could equate that to, because VD is equal to E over B, so we've got our number of electrons. We've got E over B is our drift velocity, and then we're multiplying by A. The voltage is equal to our E over L. So we can make E equal L times V, and that'll give us a current, NE LV over B times A. And if we solve for V, which is our voltage, by the way, not our velocity, this is voltage. Voltage. So we can solve for the voltage, and this is what we call the Hall voltage. So now we've got B times, not A. We've got B times I. We're going to divide by NE, L, V, and A. NE, L, V's already done, and A. So NL and A. Just real quick, NEA NEA is equal to BILV. BI over L voltage. I have that upside down. I have the length upside down. Okay, yeah, that's better. And that equals I over VD. So if we put that in here, then we end up with the V Hall is equal to our B times L times VD. Okay, that is called the Hall voltage. Okay. We did quite a bit. I don't know if I'm going to have mass spectrometer problems, even though I do like mass spectrometer problems. But let's say our B field is like this. We're shooting a charged particle in at a certain velocity here. And then, of course, once it enters the B field, it's going to want to do this thing where it rotates with around a certain circle R. And then we can have a mass spectrometer here. And then depending on masses and charges, we'll get hits in different bins. And that's essentially what it's made of, is a bunch of different bins. And then as each bin gets excited or hit, it counts. And that's the whole key. So here's mass spectrometer. The radius, we've done it a million times. The radius is M. V, not big V, not voltage. Little v, velocity. MV QB. Okay, that's our radius for a mass spectrometer. And of course, Q over M is our charge per mass, or we could invert it and have mass per charge. That's a good ratio that everybody wants to know for different items, protons, electrons, all that. Always interesting. So the mass spectrometer, very interesting device. Here's the question. How do we calculate a B field period? Like, just how do we calculate a B field? We've got moving charges, of course, because otherwise we have no B field. So we'll have moving charges, and they may be moving through wires. So we'll be looking at the current due to the wires. There's all kinds of ways to do it. To calculate the B field, I said there's all kinds of ways, but there's really two. One, the Biot-Savart method. And the second is Ampere's law. So Biot-Savart, they did experiments, they did a lot of stuff. Let's talk about the first method, Biot-Savart. They did find that, and this is all valid experiments that got them this information. So they found this, and let's talk a little bit about this mu naught over 4 pi. Mu naught is the permeability of free space or vacuum. So that's it. And then the cool part is mu naught is equal to 4 pi times 10 to the minus 7. And the units on that are Teslas, meters per amp. If you notice, this is mu naught over 4 pi. So really what we're only talking about there is 10 to the minus 7 Tesla meters per amp. So that's what that is. IDL cross R over R squared. That's our dB. So what did we do? We can then integrate, and we can say that our B field is equal to mu naught over 4 pi times the integral over the wire. Okay, so we're going along the wire of, here, let's draw the wire. And at every point along the way, we've got this DL, and we've got current going along the wire. And we want the B field at this certain point. So we've got an R. Actually, I drew the R backwards. Let's fix that. So we've got our R from there to there, and we've got our hat. Everything's known. So here's our point. So we can go through and we can do this. IDL cross R over R squared. And we just go from here to here if we want to know the B field for that wire on that point. And not terrible. One of the students asked me if there will be a problem based on this Biot-Savart method. I'm going to see if I can find something that will work, that isn't terribly difficult. That's not a hard integral here. We need an easy integral, and yet something that isn't as easy to figure out when we're doing the Ampere law way. So we can do Ampere law, Amperes. And this is a lot easier because what are we doing? We're just saying, okay, I've got some B field. I've got a closed loop around the B field. My closed loop I'm going to make easy to figure out. So let's say we've got a wire and the current is flowing straight at us, okay? And we do our closed loop in a complete circle, radius r, and we go all the way around that circle, dl, okay? And inside that loop is this current. So we've got an easy situation. We do the circumference is 2 pi r. So we've got b times 2 pi r is equal to mu naught I enclosed. How easy is this? Super, super easy. Mu naught over 2 pi r I enclosed. And we're done, right? I mean, whew. So what would you rather do? This we didn't even get to do because it's not cake, right? This is a hard problem. But this one doesn't matter as long as we make our surface, our closed surface, or not closed surface, our closed line integral. This is a line integral. So our closed line, our loop, is we can put it anywhere we want. Doesn't have to be at the center even of that current, as long as it's enclosed. And we're good to go. So that's a nice, Ampere's law makes it nice. However, there aren't very many situations where we can do Ampere's law. And if it's a general situation, we have to do this. Now, again, I am going to try and find something where we can do that in a easier situation than doing Ampere's law. And I'm not hopeful that that's going to happen, but I'm going to try. So I just want you guys to be aware of that. We talked about curved wires and doing that with different geometries. We did it. So all of that worked out. Let's raise it up a little bit. Raise the roof. Okay, so we have let's do forces between two lines. So, not lines. Forces between two wires carrying a current. So we've got two. We'll put I1 down here. We'll put I2 down there. They're a certain distance apart. We'll call it R. We can do our X and Y axis. Always good to do. What is the B field? Okay. So we want to know the B field due to the current in one of the wires. So let's just deal with the B field from 1. And we put our thumb along the current going down. So it's actually going to be coming up here out of the page. If we go to this point This is B1, okay? And we can write down what we just figured out, B1 equals I1 divided by 2 pi r, okay? We've got our next wire already next to it. It's also pointing down. So what's happening? What's the B field over at the I1? So let's figure out what B2 is. Put our thumb along and we come over here and we'll notice that B2 is going into the page at I1. So if we call, let's see, Z, our Z-axis, B1 is positive in Z, B2 is negative in Z. Okay, so what is the force of one wire on the other? Just one on the other. That's all we want to know. So the force is equal to our ILB. Everything's perpendicular to each other, so we can drop the sign of theta equals to 1. So ILB. And the force of 1 onto 2 is equal to I2 L B1. Do I have that right? I2, so the force of 1 onto 2 would be I2, that's the current flowing, the length L. So we're going to come over here and we're going to make a length L. And then times B1, and that's perfect. That nails it. So what is that force? We can even do force per length if you want. Force of 1, 2 divided by the length is just I2 times B1. Well, let's figure it out. We've got mu naught I1 over 2 pi r times I2. Pretty good. I like it. We haven't really talked about the direction yet. I want to talk about the direction because that's really a key here. And let's just talk about that. Here we have I2. Okay, it's going down. Out of the page, we've got B1. So when we do one cross the other, so we've got I2 going down. We put our fingers along I2. I cross B. Okay, so we fold our fingers up from I2 to coming out of the page B1. That puts our thumb along the direction of F12. So F12 is the force of 1 onto 2 is this direction. Now, of course, F12 is equal to minus F21. Because here, look, all these things are going to be just flipped around And we'll end up saying minus mu naught I1, I2 over 2 pi r. So the force B2, we've got I going this direction. Our force is then F21. So the direction, they're equal and opposite. In other words, we've got equal and opposite things happening here. And that's pretty cool. And, you know, I need to really, these are force per length. All right, so we'll keep the lengths in there. That's force per length. But that's a really awesome thing. But here's the other part. What defines 1 amp of current is if we were to make I1 equal I2, then we've got F21 is equal over L is equal to mu naught over 2 pi. And if we make R 1 meter, then we've got I squared. And we can then do some fancy footwork. And if we say that F over L, we can make it. We can make F over L equal 2 times 10 to the minus 7 newtons per meter. Then when we go through and do all the math, that ends up giving us I equal to 1 amp. And that is actually how we have defined 1 amp. So you take 2 wires, you put them apart, if you get a force of this per length, then your current, if your currents are, of course, are equivalent, you have a current of 1 amp flowing through them if R is equal to 1 meter. So all of that is pretty, that's pretty great stuff. We're gonna stop here and continue in a minute.